Let's do an example of working with a probability density function. In this case, let's let x be a continuous random variable whose PDF is given by this expression right here. It's x squared plus 1 over 3x squared if x is between 1/2 and 2, including 1/2 to 2, and 0 otherwise. Often we'll have PDFs like this, which are 0 except on some interval. And when that happens, I'll write this kind of more compactly by just saying the PDF is this function on that interval. And what I mean is that it's that function on that interval and 0 everywhere else. It's going to happen a lot. And I don't like writing, it's annoying to have to write out this big piecewise thing every time. So I'll just say this, the PDF of x, f, capital X of little x, is this expression on this interval. And when I say that, that means it's 0 everywhere else. Okay. So remember, this thing, this probability density function, it describes the distribution of our random variable. And the key idea here is that the probability our random variable is in any interval, say a, b. You can get that by plugging those two numbers, a and b, into the CDF and subtracting, or by integrating the PDF over that interval. Okay, this is just the fundamental theorem of calculus, actually, right? Cool, because this is the derivative of that. The PDF is the derivative of the CDF. Okay, so one thing that should be true is that if we integrate from 1/2 to 2, what's the probability our random variable takes a value between 1/2 and 2? Well, our PDF is 0 everywhere else, so it's got to be 100%. So in general, properties that all probability density functions have should be a function that is always non-negative and it encloses an area of 1. Remember, you should think of areas as probabilities when we're working with the PDF. That's the whole idea of the PDF. And that's really nice because if you look at it, it's a really nice visual representation of what this random variable's distribution is like. The fact that the PDF is higher up over here means that an interval like this, say 1/2 to 1, and compare that to an interval like this, 3/2 to 2, well, the fact that the PDF is higher over here means the random variable is more likely to end up in here than it is to end up in here. It's nice. You can interpret it kind of visually the same way you would a bar graph, right? Higher bars more often. Probability that a random variable ends up in those regions more often. Okay, so let's check that this really is a PDF, that it really, well, just look at this. It's definitely always non-negative, because this always comes out positive, and this is always 0. So let's check that it encloses an area of 1 by just doing the integral. So if we find the probability, I'll write it differently. 1/2 is less than or equal to x, less than or equal to 2. That's the same thing as saying x is in the interval 1/2 to 2, right? Just written differently, using an inequality. So if we do this, integrate from 1/2 to 2, then we should get 1. Okay, so let's integrate from 1/2 to 2. In fact, if we really were integrating over the whole real line, we should get 1. But if you were to integrate from -infinity to infinity, you know 0 area here, 0 area here. So that just turns into the integral from 1/2 to 2. That's what we're doing. Okay, so let's do this integral and just check. X squared x. Okay. So to do an integral like this, what are we going to do? Well, let's break this up into, you see once you break this up, it's going to be like a sum of powers of x, and that's going to make an easy integral. So I'm going to get x squared over 3x squared, which is just going to be 1/3. And then over in the second term, I'm going to get 1 over 3x squared, which is actually going to be 1/3 x to the -2, right? The -2 means it should be in the denominator, which is what we want. All right, and the fact that I wrote it as x to the -2 is just going to make it easier to use the power rule to do the integration. So we do an antiderivative of 1/3 x, Antiderivative of this guy, the 1/3 stays where it is, and I think, okay, what do I have to take the derivative of to get x to the minus 2? Well, when you take the derivative, the power goes down by 1, so it had to be x to the minus 1. When I do that, this minus 1 comes down, so I'll need a minus here to cancel with that. Okay, great. I think that's right. Yeah, that comes down there, it makes it positive, and then you get minus 2. And now we're going to evaluate it from 1/2 to 2. Just have to do a bunch of arithmetic now. 2/3 plus, it's 2/3, right? Plug the 2 in here, it goes in the denominator. So, and there's a negative, don't forget about that. Minus 1 over, the 2 goes in the denominator, makes a 6. Minus, now I plug in the 1/2, 1/6 plus, plug the 1/2 in here. Ooh, the minus 1 makes it a 2. There's negative, so it's minus 2/3, I guess. All right, and now I just have a bunch of arithmetic to do. So here we go. 2/3 plus minus 1/6. What is that? This is 4/6 minus 1/6 is going to be 3/6 minus, what's in here? Minus 2/3. Oh, it's like the other way around, right? With the signs. Same thing here, but the signs are the other way around. So this is going to be minus 3/6, right? And so 3/6 minus 3/6. Yes, indeed, we get 1. Good. So this is really a PDF. The area underneath is 1. Okay, and so if you want to find the probability x is in any interval, you just integrate on this interval. So let's say, another example. Let's find the probability our random variable ends up in here, between 1/2 and 1. All right, everything's all set up, so this should go pretty quick. Before we do, just look at the graph. We can already tell, we can guess what this is going to be. We've got these 3 equally sized intervals here, right? And the PDF is higher over here. So whatever this area is, there underneath the whole thing was 1. So it's definitely going to be bigger than 1/3. Yeah? So we're going to get something bigger than 1/3. Just look, comparing these two areas, if I drew this right, looks like we're not going to get like 90%, but we're going to get something much bigger than 1/3, 33%. So let's do this. Between 1/2 and 1, we're going to integrate from 1/2 to 1. Let's see, 1/2 to 1, 1/2 to 1. The antiderivative, I'm going to do everything the same. 1/2 to 1. The only difference is in here, I'm going to plug in 1. So this is going to be what? The 1/2 parts of the 1, 1/3. And then I plug the 1 in here, plus 1/3, okay? And so in here, 1/3 plus 1/3 will give me 2/3, yeah? Okay. Oh, wait, I missed a sign, right? There's a minus sign in here. That's 1/3 minus 1/3. Okay, whoops. So that's a 0. So we have 0 minus 3/6. That's just 3/6. 1/2. Okay, so it turns out the probability that x lands between 1/2 and 1 is 50%. That area is 1/2.